students, myself Rakhi Kumari, Assistant Professor in the Department of Electronics and Communication Engineering, ABS Engineering College, Ghaziabad, affiliated to Dr. APJ Abdul Kalam Technical University, Lucknow. Today in the lecture series of Microwave and Radar Engineering, I am going to teach you the left out portion of the TE modes in a rectangular waveguide, some important formulas which are required in our calculation purpose, and then I will continue with the TM modes in the rectangular waveguide. Always try to that the TE mode calculation and the TM mode calculations are always already 100%, you can say that maximum same. So, if you have not go through the TE mode in a proper way, you are not able to learn the TM modes. So, always try to complete the TE mode first and then move towards the TM mode. Now, some important terms, or we can say that important formulas which are related to the TE modes in the rectangular waveguides are, first of all, the cutoff wave number Kc for the TMN, that is Mn stand for number of half wavelength in the x direction and the number of half wavelength in the y direction. The wave number, cutoff wave number is given by Kc. The x term already we have in our expression of the field component in the TE modes, m pi by a plus n pi by b a whole square. So, for calculating the wave number, what the important thing we have to know? We have to know the dimension of the waveguide and number of half wavelength in the x direction and the y direction. So, for example, TE10, if we have that TE mode which is available with us is TE10. In that case, m is equal to 1 and n is equal to 0. We can have the cutoff wave number in this term also, where omega c is our cutoff frequency 2 pi f c and under root mu epsilon. Now, cutoff frequency for the TMN mode is given by the cutoff frequency already discussed in the last lectures and in the starting of the waveguide. That cutoff frequency plays a very important role because it will decide that which frequency will propagate, which frequency signals or which frequency waves are propagate inside a waveguide. So, this is a very important parameter and this is given by this expression 1 upon 2 under root mu epsilon under root m square by a square plus n square by b square. Now comes the propagation constant. Propagation constant. So, let us have a look at the first for your example. Let us do the calculation of the dominant mode, the most important modes on the TE mode, that is TE10. Fc is equal to what? 1 by 2 under root mu epsilon and this is m is equal to 1 by a square and this expression will be equal to 0. So, this will be Fc 1 by 2 and 1 by a. This is the frequency. So, this is a method of calculating the frequency and propagation constant is given by beta g is equal to omega under root mu epsilon under root 1 minus Fc by f, the frequency for which we are calculating the propagation constant and the cutoff frequency. Now, the phase velocity in the z direction is given by Vg is equal to omega upon beta g and it is equal to Vp upon under root 1 minus Fc by f whole square and Vp is equal to 1 upon under root mu epsilon. The characteristic wave impedance is given by Ex upon Hy or it is equal to minus of Ey upon Hx and it is equal to omega mu upon beta g and nu under root 1 minus Fc by f, and this is the intrinsic impedance of a unbounded dielectric and it is equal to under root mu by epsilon. The wavelength lambda g in the guide is given by lambda upon under root 1 minus Fc by f whole square. So, these are the common formulas or the common terms which always get encountered in the case of a rectangular waveguide. This is the expression for the TE mode. Similar expression we will have for the TM mode also. So, there is some difference in the TE mode and the TM mode expression. So, always go through the expression in detail. no, don't consider that the expression for this will remain same for the TE and TM mode, because the field components will be different for TE and TM modes. So, this expressions will also be different. So, let us have a look at some important terms of the waveguide. First one is the degenerate mode. Degenerate modes are those modes, two or modes having the same cutoff frequency. They are said to be a degenerate modes, and in rectangular waveguide TMN and TMMN are always same cutoff frequency. That is why it is called the degenerate mode. For example, if we say that T11 and TM11 will be the degenerate mode, T02 and TM02 will be the degenerate mode, but this is in the case of a rectangular waveguide. In the square waveguide, we can't able to say that T20 in the rectangular waveguide are similar. Okay, this will be not a degenerate mode, but for the square waveguide TMN and TNM, for if we, this is the case for a square waveguide, then this will be a degenerate mode. For the square waveguide, these are the degenerate modes. So whenever somebody asks you about the degenerate modes, then gets sure that whether they are asking for the rectangular waveguide or for a square waveguide. In general expression, as per this syllabus, you have to study the rectangular waveguide, but if somewhere it is asked about the square waveguide, the degenerate modes will change. Now comes the dominant mode. Dominant mode is the mode in a waveguide having the lowest cutoff frequency. Dominant mode rectangular waveguide, for A greater than B, the assumption which we have taken that if we have a rectangular waveguide and this is A and this is B, because in always the formulas come cutoff frequency, we have the A and B expression. So, A should always be greater than, if this condition is applicable, T10 is the dominant mode, and this mode will have a lowest cutoff frequency. Now, moves toward the TM mode in a rectangular waveguide. The steps will remain same as the TE mode in a rectangular waveguide. For the TE mode in a rectangular waveguide, the first step which we have done is that TM stand for transverse magnetic. Transverse magnetic, that means the direction in which our wave is propagating, in that direction our magnetic field component will be equal to 0. So, if we assume that our wave is propagating in the z direction, so in that case what the z component of the magnetic field, that is Hz, should be equal to 0. Similarly, in the case of a TE mode, Ez equal to 0, and since the wave is propagating in the z direction, so we have the only thing which is available with us is the wave equation for calculating the expression of Ez. So, we have the Ez expression of the wave equation, and already in the wave equation solution we have solved and we have obtained this expression of the Ez. This is the expression of Ez which will be used for us in the further expression. Now, so we are going to calculate get the value of Am, Bm, Cn and Dn. These are the constant and its values is decided on the basis of the boundary condition. So, the boundary condition is that the field vanishes at the waveguide wall since the tangent component of the electric field is 0 on the conducting surface. This is the boundary condition available with us. So, for Ez equal to 0 at x is equal to 0 and A, we will proceed in the same way as we have done for the TE mode, that we will substitute the value of Ez equal to 0 for particular condition, that is x is equal to 0, and after that we will have the value of Bm is equal to 0. Similarly, we will have the Ez equal to 0 for y equal to 0, and we will get the value of Dn equal to 0. And substituting the value of Bm equal to 0 and Dn equal to 0 in the expression of Ez here, we will have the expression of Ez concise now, that is this one. Now, this is one of the important question in the case of a microwave and the waveguide comes here. Ki if we know that TE10 is the dominant mode in the case of a TE modes of a rectangular waveguide. But when we see here in the case of a TM mode, here we can say that Ez is equal to EOZ, and if we are having the TM01 mode, TM01, that is sine 0, m will be 0, sine 0, the whole expression will be equal to 0, and sine whatever with the value here. But if the sine 0 comes here and it is multiplied with any component, the expression will be final 0. Similarly, for the TM10 Ez, EOZ, here comes the sign, because here it is 1, so pi x by a, but now again comes the sine 0 for this will make the Ez component equal to 0. So, this two component does not exist in the our TM modes of a rectangular waveguide, but it exists for the TE mode. But this question arises, why we are saying that TM01 and TM10 is not existing in the TM mode of a rectangular waveguide. So, for that purpose you have to solve it using the expression of Ez here, and you will get the expression as 0. So, you can say that this two component does not exist. So, finally, the conclusion comes that TE10 is the dominant mode in the rectangular waveguide. Now, del cross E, we have taken this one of the Maxwell equation, Maxwell curl equation. Del cross E is equal to j omega epsilon h. So, when we write it as a Ax, Ay, Az and del upon del x, del upon del y, del upon del z, Ex, Ey, Ez is equal to j omega epsilon Hx, Ax plus Hy, Ay plus Hz, Az. So, for your simplicity, I am just taking the Ax component. For getting the Ax component, it is equal to this one. So, in this way, and after that we will substitute what? Del upon del z is equal to minus j beta z, and since it is our TM mode, that means z component of the magnetic field will be 0, Hz equal to 0, and then I will take a y component, then del upon del x minus Ez minus del upon del z Ex is equal to j omega epsilon Hy Ay. Then Az component, del upon del x Ez minus our del upon del y Ex So, now again substituting del upon del z is equal to minus j beta j and Hz equal to 0, we will have this 6 equations with us. So, our next step that we have to calculate Ex, Hy, Hz, Hx, Hy, and Hz component is equal to 0. So, what we are going to do from the last expression, we will have the expression, and from this solving equation one by one as we have done in the T mode of a rectangular waveguide, we will able to get the expression of this Ex, Ey, Ez, Hx, Xy, and here again we are assuming that beta g square minus omega square mu epsilon is equal to minus kc square. On the T mode also we have assumed omega square mu epsilon minus beta g square is equal to kc square. Same assumption here also we are taking, and after then substituting the value of Hz which is available with us, Ez which is available with us in the expression of all the expression, and considering all the constant as in the Ex, if the constant exit, by considering all the constant as Eox, and in Ey considering all the constant as Eoi, we have get the all the expression of the Tm modes of a rectangular waveguide. Now, here the same thing for the T mode, as we have got the formulas, important formulas, same thing we have for the Tm mode also. For the Tm mode, Fc is basically the same as the T mode expression for the Fc, that is the cutoff frequency, and this is equal to 1 upon 2 under root mu epsilon under root m square by a square plus n square upon b square, and beta g, that is propagation constant, is equal to omega under root mu epsilon under root 1 minus Fc by f, where Fc is our cutoff frequency and the f is the frequency propagating inside a waveguide. Lambda g is equal to lambda under root 1 minus Fc by f whole square. Velocity is equal to Vp, and this is equal to under root mu upon epsilon 1 under root 1 minus Fc by f whole square. And this is our characteristic impedance, which is given by beta g upon omega epsilon, and this is our intrinsic impedance. Now, one numerical related to the waveguide. An air-filled rectangular waveguide of inside dimension this. So, already we note for the T modes in the rectangular waveguide, we have A is greater than B, that means A is here is equal to 7 and B is equal to 3.5, both are the unit is centimeter here. Now, the cutoff frequency, find the cutoff frequency and determine the phase velocity of the wave and the guide at a frequency of 3.5 gigahertz. The frequency which is propagating inside the waveguide is 3.5 gigahertz, and in the third step determine the guided wavelength. So, here we are calculating it for the T mode and for the air filled waveguide. So, the formula for Fc, if we are remembering the formula of Fc, what is here for the T mode? Fc is equal to 1 upon 2 under root mu epsilon m square by a square plus n square by b square. So, from where we will get the c by 2a, the formula which is here used here. And the place of mu, we can write mu r, epsilon r, mu naught, epsilon naught, and m is T10 mode, m is equal to 1 and n is equal to 0. So, this will be equal to 1 upon a square. So, 1 upon 2, since it is the air filled waveguide, so mu r or epsilon r is equal to 0. So, what is here? Under root mu naught epsilon naught and 1 by a by taking under root of 1 by a square. We know that under 1 by under root mu naught epsilon naught is equal to c, that is the velocity of light. So, now we are getting the expression which is used in the formula here, that is for the, so the cutoff frequency formula for the TE mode of a rectangular waveguide is the TE10 is the C by 2A. So, just substitute the formula, values of C and A, we are having the cutoff frequency as equal to 2.14 gigahertz. Now, the second thing which we have to calculate is the phase velocity of the wave in the guide at a frequency of 3.5 gigahertz. So, Vg is equal to C upon under root 1 minus Fc by A. We are taking it C because this is the air field waveguide, otherwise it will be equal to Vp, and it depends upon the, of course, value of the relative permittivity and the absolute permittivity of the dielectric medium used. Then substituting the formula, we have this. Then the guided wavelength, this is the formula for guided wavelength. You have the value of lambda naught C divided by frequency which is have at which the waveguide is, in which the frequency which is inside the guide, that is equal to 3.5 into 10 to the power of 10 to the power of 8 under root 1 minus Fc upon F. So, this is our lambda g. So, here comes the end of the T and the TM modes of a rectangular waveguide. In the next class, we will study about the power of the power transmission and the power losses in the TE and the TM mode. Thank you for attending today's lecture.